cosmos is a tapestry woven from time and light, and for decades, humanity has only been able to glimpse the final patterns. But then came the James Webb Space Telescope, JWST, a machine built not just to look, but to look back. It was designed to pierce the veil of the universe's infancy, a time when the first stars flickered and the first galaxies were mere cosmic wisps. When the James Webb Space Telescope began observing the early universe, the images it sent back were not merely photographs. They were chronological artifacts. They revealed a frantic, complex, and deeply unexpected cosmic frontier. And within these unprecedented deep fields, astronomers noticed something startling: a dense population of intensely compact and vibrantly red galaxies. They called them the little red dots. These objects were not just faint, they were anomalies. Their properties didn't just nudge against what our current cosmological models predicted for that primordial era. They fundamentally challenged them. These little red dots, appearing at the very dawn of creation, were too compact, too bright, and too energetic to fit neatly into the established narrative of early galaxy evolution. A recent, groundbreaking study led by the astrophysicist Andres Escala proposes a radical solution to this cosmological puzzle. Escala suggests that these little red dots may not be simply one type of object, but rather represent a pivotal, transient phase, a transitional link that bridges the gap between the densest, most ferocious star-forming galaxies and the very earliest, most colossal, supermassive black holes. If the vastness of space fascinates you as much as the mysteries hiding within it, you're in the right place. Subscribe to Stellify Science and join our voyage through the stars, where every discovery brings us one step closer to understanding the unknown. In this video, we at Stellify Science are going to embark on a journey of cosmic origins. We will look at the specifics of what was discovered, dissect the baffling evidence that pits two major scientific interpretations against each other, and finally, explore the revolutionary new evolutionary model that Escala and his team propose. We'll look at why these fleeting objects matter profoundly for understanding the entire history of galaxy and black hole evolution, and what comes next in this exhilarating line of research. This is the story of how JWST may have just found the missing link, the actual seeds of supermassive black holes. Let's get started. The first detection of the little red dots was announced in late 2022, a moment that instantly redefined the goals of modern astronomy. They emerged from James Webb Space Telescope's early deep field surveys, observations designed to stare into the seemingly empty patches of sky, letting light from the most distant corners of the cosmos trickle in over hundreds of hours. The sheer distance of these sources is critical to understanding their significance. They appeared at extremely high redshifts, specifically between Z04 and Z8. Let's quickly contextualize what this means. Redshift is the cosmological measure of how much the light from a distant object has been stretched by the expansion of the universe as it traveled toward us. A higher redshift means a greater distance, and crucially, a deeper look back in time. A redshift of 0.4 places these objects at about 1.5 billion years after the Big Bang. A redshift of 0.8 pushes us back to an astonishing 600 million years after the Big Bang. To put that in perspective, if the 13.8 billion year history of the universe were compressed into a single calendar year, we would be looking at objects formed around mid-January. We are seeing these systems as they existed just 4 to 11% of the way through cosmic history. Their physical properties immediately screamed anomaly. First, they were extremely small. While a typical star-forming galaxy in the early universe might stretch across several thousand light years, These little red dots were often just a few hundred light years across. They were ultra-compact, dense pockets of matter unlike anything seen before in such numbers, at such a profound look-back time. Imagine compressing the entire stellar population of a modest galaxy into a space barely larger than a single star cluster in the modern Milky Way. That's the scale of concentration we are talking about. Second, they were intensely red in JWST's sensitive infrared filters. This wasn't just a faint blush. It was a deep infrared glow. This redness is a signature that astronomers use to infer composition and activity, and in this context, it pointed to two powerful possibilities at their cores. Either an enormous amount of obscuring dust, which absorbs the blue and visible light from young stars and re-emits it in the infrared, or, alternatively, energetic processes driven by accretion, the telltale sign of an actively feeding black hole. The sheer numbers of these objects, coupled with their unique, conflicting characteristics, made it clear that they represented a major unrecognized population in the infant universe. The initial data split the astronomical community into two main interpretive camps, each trying to explain this new cosmic population. The scientific challenge presented by the little red dots was the ultimate chicken or the egg problem for cosmology. Were they powered purely by stars, or were they already hosting monstrous black holes? The first interpretation posited that these dots were what are known as ultra-compact, dusty, star-forming galaxies. This model viewed the intense redness and brightness as entirely stellar in origin. In this scenario, the little red dots are the densest, most efficient starbursts in the young universe. Their cores are regions of such intense stellar activity that they are forming stars at rates hundreds, or even thousands of times faster than the Milky Way today. This frantic stellar birth creates an immense amount of dust, the byproduct of exploding massive stars. This dust then wraps the galaxy in a thick, obscuring shroud. The light from the young, hot blue stars, which are typically the most visible, is absorbed by this dust shroud. The dust heats up and re-radiates this energy, but it does so at much longer, redder infrared wavelengths. This is why the little red dots shine so brightly in JWST's infrared filters. If this model is correct, it means that star formation in the early universe was vastly more concentrated and much more rapid than current models suggest. These systems would represent the very first, highly efficient building blocks of more massive galaxies, cosmic factories that churned out stars in a concentrated frenzy. The alternative interpretation was far more dramatic, that these little red dots were, in fact, early active galactic nuclei, AGN systems, each hosting a massive black hole, MBH, at its center. In this view, the black hole's accretion activity, the process of gas and material spiraling in, is the dominant power source. This interpretation found strong support in the complex spectroscopic data returned by JWST. Spectroscopy, the analysis of light's color and intensity, revealed key fingerprints in the light from many of these red dots. Specifically, many of them showed broad Balmer emission lines. Balmer lines are hydrogen spectral features, and when they are broad, it indicates that the emitting gas is moving at extremely high velocities. In an astronomical context, these high velocities are typically caused by intense gravitational binding or rapid orbital motion in the immediate vicinity of an active, massive object. The most powerful engines in the universe capable of producing such spectral signatures are accreting black holes. The broad lines, therefore, appeared to be the smoking gun for black hole activity. Furthermore, this model required the black holes in these early galaxies to be unusually massive compared to their hosts. In the modern universe, the central black hole mass is typically around 0.1% of the total mass of its host galaxy. For the little red dots, however, the observed energetics suggested that the black hole could account for up to 10% of the total galactic mass. This massive black hole interpretation offered a direct clue to one of cosmology's greatest riddles. How did supermassive black holes grow so astonishingly fast in the early cosmic timeline? If they started out already disproportionately massive, their rapid growth into multi-billion solar mass behemoths becomes slightly easier to explain. The problem, however, was that neither scenario could account for all the observational data. The little red dots existed in a frustrating gray zone, containing spectral and photometric features that seemed to simultaneously support and contradict both the stellar-only and the black hole-driven models. The spectroscopic data, the high-velocity Balmer emission lines, strongly suggested black hole activity. But if they were truly powered by an active galactic nucleus, astronomers expected a massive, unmistakable signature of high-energy radiation, significant X-ray emission. When matter falls onto a black hole, it forms an accretion disk that heats up to millions of degrees, generating intense high-energy radiation, including X-rays. Yet, when powerful X-ray observatories like Chandra were pointed at these little red dots, most showed little or none of the expected signal. The engine appeared to be running, but the fuel wasn't igniting the way it should have. This lack of strong X-ray signatures was the most challenging obstacle for the MBHA's-AGN interpretation. It was like seeing the movement of a massive celestial clock, but hearing no tick. Conversely, the data for the purely stellar interpretation also presented a near insurmountable hurdle: the extreme velocity dispersions. Velocity dispersion is a measure of the spread of internal velocities within a system. Essentially, how fast the stars and gas are randomly moving relative to each other. The high velocity dispersions observed in the little red dots would be incredibly difficult to sustain in a purely stellar, gas-driven starburst system, without the dominant, concentrated gravitational influence of a massive object at the center. In a simple starburst, the material would fly apart too easily. The sheer, concentrated gravitational binding required to hold these systems together and generate the observed velocities pointed strongly away from a simple star formation scenario. Their unusual combination, small size, intense redness, high internal velocities, and weak X-rays, pointed inexorably to something else entirely. It suggested that astronomers were not looking at two distinct, stable categories, starburst versus AGN, but rather at galaxies caught in the middle of a profound and rapid transformation. They were observing an ephemeral stage, a cosmic caterpillar becoming a butterfly, captured halfway through the process. This is precisely where the new evolutionary model proposed by Escala's team comes in. It's a synthesis, a new track that resolves the conflict by turning the two competing explanations into two successive stages of the same single, rapid process. The core insight of the Escala model is recognizing the instability inherent in the ultra-compact, dense starburst scenario. These systems, packed with stars and gas in a tiny volume, are gravitationally top-heavy. They are not built for long-term stability. The model proposes a three-stage evolutionary track. Stage 1. The dense, star-dominated precursor. The process begins exactly as the stellar-only model describes. These systems form as extremely dense, star-dominated galaxies. The intense star formation provides the infrared glow and the initial redness due to dust, making them visible to JWST. At this stage, they are structurally compact, leading to a high initial velocity dispersion, driven by the collective gravity of the concentrated stars and gas. Stage 2. Core collapse and black hole. Seeding. This initial stage of instability cannot last. Over cosmic time, and likely very quickly, the high central densities cause the inner regions of the galaxy to undergo a catastrophic gravitational collapse. This collapse has a twofold effect. It either directly creates or rapidly grows a massive black hole at the galaxy's center. The dense stellar material, either through repeated stellar collisions or the infall of enormous gas clouds, provides a direct, efficient path for a massive black hole seed to form and begin accreting material. Crucially, in this phase, the black hole is growing and influencing the system's dynamics, thus explaining the high internal velocities and broad Balmer lines. But it is still deeply embedded within the dust and gas shroud. The infalling material has not yet cleared the immediate area, and the accretion disk has not yet fully stabilized and heated to the temperatures necessary to produce the powerful X-ray jets and high-energy radiation characteristic of a fully turned-on AGN. The black hole is active, but muffled. It is a pre-AGN stage. Stage 3. The ignition and transformation to AGN. Finally, the black hole reaches a critical mass and accretion rate. It begins to expel powerful outflows and jets, which rapidly clear the surrounding gas and dust. The accretion disk stabilizes and the system ignites, transforming the object into a fully fledged, recognizable active galactic nucleus, complete with strong X-ray emission. By connecting the stellar-only Stage 1 and the MBH-AGN Stage 3 scenarios via a transitional phase, Stage 2, Escala's theory transforms the little red dots from baffling outliers into expected critical waypoints in the grand flow of early galaxy evolution. This synthesis elegantly resolves the main paradoxes. The absence of strong X-rays. This fits perfectly with the idea that many little red dots are caught in the short-lived, deeply shrouded pre-AGN stage, Stage 2, before the black hole fully lights up. The extreme velocities. These are explained by the enormous, concentrated gravitational potential of the ultra-compact stellar core and the already growing black hole, which is influencing the dynamics even before it becomes luminous. Furthermore, the model explains their scarcity at lower redshifts, later cosmic times. If this is a brief, highly unstable phase, lasting perhaps only a few tens of millions of years, then we should only see them during the universe's earliest epochs, when the conditions for such rapid, massive collapse were common. The little red dots, under this interpretation, are not random cosmic specks. They are the observational window into the genesis of supermassive black holes. If this interpretation holds, the little red dots are more than just a transitional phase. They offer a direct, observational glimpse into the foundational process that shaped the universe as we know it today. Their discovery helps address one of astronomy's biggest, most vexing open questions. How did black holes reach masses of 1 billion solar masses, or more so early in cosmic history? The problem of the early monster black holes has haunted cosmology for over a decade. Finding black holes with masses equivalent to billions of stars, when the universe was less than 1 billion years old, requires a mechanism for growth that is almost impossibly fast. Standard models suggest that black holes grow by slowly accreting gas from their surroundings. To reach such massive sizes so quickly, they would either need to start with unnaturally large seed masses, the so-called heavy seeds mechanism, perhaps formed by the direct collapse of massive gas clouds, or they would need to accrete matter at a nearly constant, hyper-efficient rate, a process known as Eddington-limited accretion, for hundreds of millions of years, which is difficult to sustain. The little red dots suggest a natural efficient pathway, ultra-dense stellar environments. If black hole growth indeed begins in such ultra-dense stellar furnaces, The process of core collapse and direct infall provides a massive, immediate, and concentrated source of fuel. The little red dots, therefore, could represent the very earliest, heavy seeds of the supermassive black holes we see anchoring mature galaxies today. This mechanism would explain their rapid emergence without requiring exotic one-off collapse mechanisms or impossibly sustained high-rate accretion. The seeds form, in a sense, autonomously from the inherent instability of their superdense host galaxy. The discovery also profoundly challenges how we model the coevolution of galaxies and black holes. In the local, modern universe, a fundamental relationship holds. The mass of the central black hole scales closely with the properties of its host galaxy, particularly the velocity dispersion of the stars in the galaxy's bulge. This tight correlation suggests that galaxies and their central black holes grow in parallel, influencing each other over cosmic time, maintaining a proportional relationship. However, the little red dots, with their proposed black hole masses, up to 10% of their host galaxy's total mass, shatter this relationship. If the black holes in the early universe were proportionally much more massive, 100 times more massive relative to their hosts than today, it means that the relationship between galaxies and their central black holes must have evolved over time. Instead of coevolution, the early universe may have been governed by a black hole-led growth model. The early black holes, disproportionately massive, may have acted as the primary architects, shaping and influencing the growth and star formation of their host galaxies, rather than simply growing passively alongside them. This has vast implications for how we understand the cosmic feedback mechanism, the way energy and matter from the AGN influence and regulate star formation in the surrounding galaxy. Recognizing this transitional pre-AGN stage can fundamentally refine how astronomers classify early high redshift infrared sources. Some faint red objects that were previously dismissed as simple dusty starbursts may in fact be active seeds caught in the stage 2 transitional phase. We are, in essence, developing a new dictionary for the first generation of galaxies. The Escala model is a powerful hypothesis, but it remains just that, a hypothesis, until confirmed by further multi-wavelength observations. To test these revolutionary ideas, astronomers are focusing on several aggressive observational strategies, primarily leveraging the incredible sensitivity of JWST in conjunction with other world-class facilities. The most immediate test is to push the sensitivity limits on the high-energy side. Astronomers are conducting unprecedentedly long, deep X-ray observations using facilities like the Chandra X-ray Observatory and, in the future, next-generation X-ray telescopes. The goal is not to find the expected strong X-ray signal of a fully active AGN, but rather to detect the weak accretion signals characteristic of a highly obscured, low luminosity, or merely nascent black hole. The subtle heat signatures of the pre-AGN phase, stage 2. If a large sample of little red dots, which show broad Balmer lines, also show a consistent weak X-ray signal that is nonetheless higher than expected for a purely stellar system, it would be a powerful confirmation of the transitional stage. JWST's instruments, particularly its spectrographs, will be tasked with more precise measurements. Infrared spectroscopy will be used to better constrain 3 critical parameters simultaneously. Velocity dispersions. Pinning down the exact internal velocities will quantify the required gravitational potential. Verifying if the mass needed to sustain the movement can be attributed solely to stars or necessitates a substantial black hole component. Gas content. Analyzing the gas in the core will help determine the available fuel supply and the efficiency of the star formation process. Stellar masses. Refining the stellar mass of the host galaxy is paramount to accurately determining the black hole-to-host mass ratio, the 10% versus 0.1% figure, and charting the evolution of this vital relationship. While X-rays trace the very inner accretion disk, radio and submillimeter observations may reveal the signature of growing black holes at a slightly larger scale. Black holes, as they accrete matter, often launch powerful collimated jets or less focused outflows that push gas away from the galactic center. These outflows leave distinct spectral and morphological signatures in radio wavelengths. Facilities like the Atacama Large Millimeter Submillimeter Array, ALMA, and the upcoming Monumental Square Kilometer Array, SKA, will be essential. SKA, with its unparalleled sensitivity, promises to increase the number of detectable radio sources in the early universe, potentially revealing jets associated with pre-AGN little red dots and providing statistical context. Future space missions will dramatically increase the sample size and provide the necessary statistical power to truly test the evolutionary track. The Nancy Grace Roman Space Telescope, often called Roman, with its massive wide field of view, will survey huge swaths of the sky, discovering thousands more high redshift objects. This will be crucial for determining the true population density and distribution of the little red dots, providing the statistical framework needed to solidify their role as a required phase in early galaxy formation. Finally, determining how long the little red dot phase lasts will be a key measurement. If it is confirmed to be a short-lived phase, perhaps just 10 to 50 million years, this brevity would logically explain why these objects are so rare and are only visible at the highest cosmic times. Pinning down this crucial timeline will help refine galaxy formation models, clarifying precisely how quickly black holes can emerge from dense stellar environments and begin to dominate the cosmic landscape. The little red dots, observed by James Webb Space Telescope, are far more than just new entries in a cosmic catalog. They are, in all likelihood, the observational evidence for a crucial transitional stage between the most ultra-dense star-forming galaxies and the first truly massive black holes. Their short-lived and turbulent nature explains why they have eluded detection until the unparalleled infrared power of JWST was brought to bear. These compact, red, and highly energetic objects may represent the missing link, the definitive physical mechanism, to understanding how the foundational seeds of supermassive black holes formed, and how galaxies and black holes initiated their complex, codependent relationship in the young universe. They are the seeds of the universe's greatest engines, captured at the moment of their awakening. The journey to understand the cosmos is one of perpetual revision, and the little red dots have forced us to tear up the old maps and draw new ones, placing the formation of supermassive black holes earlier, more efficiently, and more inextricably linked to the very first dense clumps of stellar matter than ever before. This is science at its most revolutionary, the observation dictating the theory. If you found this exploration into the cosmic dawn and the genesis of black holes fascinating, then you're in the right place. We at Stellify Science are dedicated to bringing you the most groundbreaking, frontier-pushing discoveries from the James Webb Space Telescope and beyond. Don't let the next chapter of cosmic evolution pass you by. Be sure to hit that like button if you enjoyed this video, and subscribe to Stellify Science right now. Hit the notification bell to join our community and never miss a deep dive into the mysteries of the universe. Tell us in the comments below, do you think the black holes formed first and drove galaxy growth? Or did the galaxies drive the black hole growth? Let's discuss it. Thanks for watching, and we'll see you in the next corner of the cosmos.